In this lesson, we're going to look at area bounded by a curve and the x-axis. So we're going to start just by thinking about why an integral gives the area bounded. So if we take, let's use the idea of Riemann sums. If we take this area of unknown shape and we divide it into shapes that we know we can calculate the area of. So for example, perhaps we divide it into n rectangles, okay? And so let's let A be x sub 0. That'll be our first x sub 1, x sub 2, x sub 3, and maybe I'll make a big rectangle here so I can sort of describe what's going on there. Okay, all the way up to, we've divided this into lots of rectangles. And let's say our last rectangle is our nth rectangle. Okay, so in general, we would say that the area bounded by the curve and the x-axis can be approximated by adding up the areas of the rectangles. Starting at our first rectangle and going to our nth rectangle. And we know that the area of a rectangle is base times height. I'm going to write height times base. Base. So let's see if we can explain how we come to the formula for the integral, how that formula becomes the integral. So let's assume that we've divided our area into n rectangles. And these are, let's say these are equal subintervals. So this distance here in my picture is the same. Let's say it's the same for each rectangle, okay? The width of our rectangle, or the base of our rectangle, okay, is going to equal b minus a divided by however many rectangles we have. And let's call that delta x. Again, this is assuming that we have even subintervals, then b minus a divided by n gives us delta x. Okay, now, what about the height of our rectangle? Okay, let's say, for example, that again, I'm going to sort of draw a bigger one so I can talk about this here. Let's say that, let me fix my drawing here. Okay, let's say that this is the ith rectangle. Maybe it's the 8th or the 9th, or maybe it's the 100th rectangle. Okay, I'm going to call this xi, which would make this xi minus 1, okay? Now, we've already designated that because these rectangles are all of equal width, we can calculate the base of our rectangle, delta x, by subtracting a from b and dividing by n. Now, the height of our rectangle, well, how are we going to find that? The height, well, let's call the height of this rectangle the place where the rectangle touches the curve. And this value can be anywhere along the bottom, can correspond to anywhere along the bottom of the base of this rectangle. So the height is a y value, or I'll say an f of x value. And let's call that f of xi star. So where xi star is somewhere between xi minus 1 and xi. And so, for example, if I were talking about this rectangle over here, xi star could be anything between x3 and x4, including x3 or x4. It would be x3 if it were a left-hand Riemann sum, and x4 if it were a right-hand Riemann sum, but it really doesn't have to be either left or right. It could be any value in there. So what does that do to our equation? So now we're saying that the area is approximately the sum of the areas of our rectangles from the first to the nth, where the height is f of xi star and the base is delta x. Now, what makes this approximation more accurate is having more rectangles. And if you have more rectangles, then your delta x becomes smaller and smaller and smaller. And what will make our formula the most accurate is if our rectangles become infinitely thin. Delta x approaches 0. Or another way to say that is the number of rectangles approaches infinity. Okay, so our area will be exactly the value of the limit as the number of rectangles approaches infinity of the sum of the areas of those infinite rectangles. And when we actually apply this limit, our sigma, which is a summing tool, becomes the summing tool in calculus, which is the integral from a to b of f of x, and our delta x becomes dx, or an element of x, an infinitely small element of x. And that's why the area bounded by the curve and the x-axis equals the integral, as long as f of x is not negative. Okay. So let's do some problems. So we're going to find the area of the region bounded by the square root of x plus y equals 6, and x equals 1. Now it's very important that we get the graph right. That's so critical here. So let's draw a graph. Let's see here. I have a square root function. Okay. I have the line y equals negative x plus 6. It might be useful for us to find the intersection between these two. So I'm going to set the y's equal to each other. Am I? Or... yeah, I can... oh, I'm... sorry. I'm going to, set the y's equal to each other. So I have root x equals 6 minus x. Let's square both sides. And I have x equals 36 minus 12x plus x squared. So then I have 0 equals x squared minus 13x plus 36. That's x minus 9, x minus 4, and I have x is 9 and 4. Well, you can see that one of these solutions is extraneous because if you think about our graph here, this is x is 6. And so I'm going to draw this line with a slope of 1 and a y-intercept of 6. And you can see that this point here is going to be 4, 2. Why did I get this other answer? X is 9. Remember that over in this step here, I squared both sides and I introduced an extraneous solution. When you square an equation, you can introduce an extraneous solution. So that's the X is 9. Okay, so, and then I have one more curve here, which is X is 1, and that is going to be right here. Okay, now, the region bounded by all three of those curves is in the middle here. Again, very important to get the graph right so that when you set up your integral, you have the limits of integration done properly. Okay, so I am all set with my graph and I'm ready to set up an integral. When you're integrating area, remember area can be done two ways. It can be done in the x, in terms of x or in terms of y. Usually one way is sort of easier than another. A problem is often set up sort of for one way or the other. And this is a good example of that. It's definitely going to be easier to integrate in terms of x here. Okay, how do you know that? Well, when I think about dividing this up into rectangles, I want to slice up and down. If I slice up and down, then I will always be starting at this line and ending at the square root function. Okay, so my rectangles are going to look like this. Now, these are infinitely skinny rectangles, right? I'll kind of exaggerate it a little bit, but remember, these are infinitely skinny. And how skinny are they? Well, the base of these is dx, and the height is the y value. Well, in this case, the height is the top y value minus the bottom y value. The top y value is the line. So the top y value is 6 minus x. And the bottom y value is the square root function, or the square root of x. So now I'm going to set up my integral. I have the integral from, well, since I'm integrating in terms of x, everything should be in terms of x. So what are the x values for my shaded area? The x values go from 1, that's the lowest x value, to 4, that's the highest x value. So those are my limits of integration. And then top minus bottom is going to be 6 minus x minus root x. So again, this is the top curve, and this is the bottom curve. Okay, so now I'm going to integrate, and I have 6x minus 1/2 x squared minus 2/3 x to the 3/2 from 1 to 4. And this is going to be 24 minus 16 divided by 2 is 8. This is minus 16/3. And now plug in the 1. Minus 6 plus 1/2 minus 2/3. And when we combine all that, you'll see, what do we wind up with here? We wind up with 4 9/2. Okay. All right, moving on. Okay, find the region in the first quadrant bounded by y equals x squared and y equals x to the fourth. So when you're graphing, I think it can be useful to first figure out, well, where do these things intersect? Y equals x squared is a parabola, and y equals x to the fourth is a similarly shaped curve, parabola shaped, right? X to the fourth means it grows more quickly than x squared, so it would look skinnier. So first of all, we're focusing only on the first quadrant. That's good. And when I look for intersection points, I set the equations equal to each other. X squared equals x to the fourth. I can move everything over to one side and factor. And then I can further factor x squared minus 1 into conjugates, x plus 1, x minus 1. And so I get 3 values for x for intersection points. And I don't really care about -1, because remember, we're only looking in the first quadrant, so that's irrelevant for me. So I only need the points x is 0 and x is 1. And of course, to get the ordered pairs, you plug the 0 and the 1 back into either of those two equations. So I'm going to have a graph that looks like this. I'm going through the point 0, 0, and 1, 1. Please make sure you either include a scale on your graph, or you can label points like I've done here, one or the other. Okay, now you need to figure out what goes where. So both of these graphs are concave up. One of them has to be below the other one, and you want to make sure you know what's what. So, okay, this graph here, let's say I take the number x is 1/2. Well, 1/2 squared is a fourth, and 1/2 to the fourth is a 16th. So this must be 1/2 1/16, and this must be 1/2 1/4. So on top is y equals x squared. On the bottom is y equals x to the fourth. Now, this integral can be easily written in either x or y. So since x is already solved for, I'm going to start by writing that way. So I'm going to say that, now remember, my shaded region is here, and my slice is here. There's a slice. And my slice, how thick is my slice? Think of the rectangles from Riemann sums. That's dx thick. That is really, really, really skinny. It's a tiny, tiny, tiny little bit of x thick. So I'm going to say that the integral, the area equals the integral from x is 0 to x is 1 of the top y value minus the bottom y value. That's x squared is on top, x to the fourth is on the bottom. So this is top minus bottom, or the bigger y value minus the smaller y value. So that gives me 1/3 x cubed minus 1/5 x to the 5th from 0 to 1, which is 1/3 minus 1/5, which is 2/15. That would be in units squared because we're talking about area. Now, I also could do this in terms of y. And what I mean is, if you think about splitting our yellow region up into rectangles, I could slice sideways as well, and that would be a perfectly acceptable way to do the problem. Now, if I do everything in y's, then I have to think of this parabola as x equals y to the 1/2. I have to solve for x, and this equation becomes x equals y to the 1/4. And now when you set up your equation, the limits look the same, but this is now y equals 0 and y equals 1. And now you're doing right minus left, the big x value minus the small x value. So that is y to the 1/4 minus y to the 1/2. Again, that is the right x value minus the left x value. And so that integrates to 4/5 y to the 5/4 minus 2/3 y to the 3/2 from 0 to 1, which is 4/5 minus 2/3, or 12 minus 10/15, or 2/15, which is exactly what we got the first time, which is, of course, what we should be getting regardless of which method we use. Okay, so now we're going to find the area of the region bounded by x equals 1 plus y squared and x equals 10. Okay, so x, let's start with our graphs. I'm going to write this as x minus 1, x minus 1 equals y squared. Okay, x equals y squared is a sideways parabola. So hopefully you remember that. It looks like that. And this minus 1 is going to shift this graph 1 unit to the right. And then, of course, the second curve, x equals 10, is a vertical line. So my graph looks like this. And then here is the line, x equals 10. Okay. And this is the region bounded. Okay. And then, okay, now, we can do this two ways. And I will write out the equation two ways. First of all, we can use symmetry, and let's do this a couple of ways. So let's start with x equals. If you look at both of our equations, x is solved for in both equations, which means we are ready to write this integral in terms of y. So when you're writing an integral in terms of y, remember your slices are going sideways from right to left, and it's your right x value minus your left x value. Okay, so everything is in terms of y. So I need to know what are the y values important to this problem. So I need to know this y value and this y value. Because there is symmetry, I know that they are the positive and negative of each other. But to figure that out, I'm going to find the intersection points of the two curves. So I have 1 plus y squared equals 10, or y squared equals 9, so y is plus or minus 3. So this is 10, 3, and 10, negative 3. So for this integral, the y values go from negative 3 to 3. And now I want to do my right x value minus my left x value. My right x value is 10, that's the line. My left x value is 1 minus y squared. So this is your right x value minus your left x value. Okay. Right x value minus left x value. And then I can quickly integrate this. This is going to be 10y minus y plus 1/3 y cubed from negative 3 to 3. Now, I'm going to solve that in a moment, but I just want to point out that I also could have done this slightly differently. And let me just make a little space here. I also could have said, okay, well, I know that this section here is symmetric to this section here. So I could have just done the top half, and I could have said, well, this is the same thing as 2 times the integral from 0 to 3 of 10 minus 1 minus y squared dy. And that's kind of nice because then when I integrate it, I get 2, and then I only have to plug in a 3. A 0 is always nice to plug in. Okay, and I'm going to get here, let's go back. What am I going to get here? I'm going to get 2 times 30 minus 3 plus 9. And so I wind up with 36 times 2, 72. Okay, 72 is what I wind up with. Okay, so moving on here. Oh, actually, it looks like I made a little mistake here. Let's go back and fix this. This should have been, right at the beginning, this should have been an x plus y squared, which would make this minus and minus. Let's go back and fix all of these. Sorry, got to fix a couple of these so we can get our answer, our correct answer. Okay, so going back, this should be a minus here, and this should be a plus here. And so that would be a minus here and a minus here. Okay, that seems better. So we have 30 minus 12, which is 18 times 2, and we get 36. Okay, that feels better. And just to confirm, we get the same thing. You know, I could show you we're going to get the same thing over here, which is 30 minus 3 minus 9. And then I'm going to have the opposite sign on everything here. So this is going to be minus negative 30 plus 3 plus 9. And so I'm going to have, what is that, 60 minus 6 minus 18. Or 60 minus 24, which is 36. Okay. And we match. Okay, I just want to point out one other thing we could have done on this problem. And let's go back and look at that graph again. So looking at the graph, you could also do this in terms of x. We did it in terms of y, but you could do it in terms of x, and you could do this also several ways. So that would mean you're slicing top to bottom. Now, without using symmetry, for top to bottom, remember, it's the y on top minus the y on the bottom. Well, now if let me put my limits here. X is going from 1 to 10 here. Oops, to 10. And I need to know what function is on top and what function is on the bottom. So when I solve for y in the equation for the sideways parabola, I get y squared is x minus 1, or y is plus or minus the square root of x minus 1. It's important to recognize that there is a plus and a minus. Okay, so this top half of the parabola, that is the plus. So that is y equals positive root x minus 1. And then the bottom half down here is the negative square root. So that is y equals negative root x minus 1. Again, this is two separate functions. Y equals negative root x minus 1 is the bottom half of this sideways parabola, and y equals positive root x minus 1 is the top half of this sideways parabola. And so now, if we were going to write the integral in terms of x, you have the integral from x is 1 to x is 10 of your top y value minus your bottom y value. So that's root x minus 1 minus negative root x minus 1, which is, of course, just going to become a plus here. And so we're going to wind up with the integral from 1 to 10 of 2 root x minus 1 dx, which is the same thing we would have gotten if we just had said, okay, well, let's do it in terms of x, but let's just do 2 times the top half, and 2 times the top half because of symmetry. And of course, you'll see that we're going to get 2 root x minus 1 integrates to 2/3 x minus 1 to the 3/2 from 1 to 10, which gives me 4/3 9 to the 3/2 minus 0, which is 4/3 times 27, which is 36. The same answer we had previously, which is, of course, what we want. Okay. So here we have x equals y to the 2/3. X minus y is 2, and y equals 8. I like to do a little sketch before I draw my real graph if I'm not quite sure how everything is going to fit together. X equals y to the 2/3. So let's see. This is, well, maybe you remember what y equals x to the 2/3 looks like. It looks like a bird. It always makes me think of like a seagull. Those paintings of seagulls where they're just tiny little dashes in the sky. Well, x equals y to the 2/3 is that sideways. So it looks like that. And then we have a line, y equals x minus 2. So that's going to be like that, something like that. And then y equals 8. Y equals x minus 2 and y equals 8 is going to be a horizontal line. Oh, I knew something seems wrong there. -2 is the y-intercept, so it's going to be like that. There we go. And then y equals 8 is like that. Okay, so now I've got an idea of what's what here. I think right now I want to find some intersection points. I want to know where do these two intersect? So I'll start there. I'm going to set the x's equal to each other. So I'm going to say y to the 2/3 equals y plus 2. That actually looks a little bit messy, but I can just see right off the bat where that's going to be. That's going to be at 1, -1. So this is a true statement when y is -1, right? You can see there's only one intersection point from the graph. So if I plug in a -1 here, -1 to the 2/3 equals -1 plus 2. Well, this is 1 equals 1. So this is 1, -1. Okay, great. And of course, this is when y is 8, that's going to be 10/8. Okay, so I'm going to draw a slightly better picture here. Oh, I'll get one more here. When I plug y is 8 into this equation, I get 4. X is 4. So this is 4, 8. Is that right? Y is 8. Yeah, 4, 8. Okay, so let me draw a better picture here, a more accurate picture now. So okay, so there is my region. Okay, I'm going to label some points on here. So this is 1, -1. This is 4, 8. This is 10, 8. And then, of course, we have 0, 0. Okay, now, you definitely want to really think about, there is one easy way and one very hard way to do this problem. And that is, should you do it in x's or y's? You definitely want to do this in y's. If I slice sideways, meaning right to left, every slice starts on the same curve and ends on the same curve. Every slice starts on x minus y equals 2 and ends on x equals y to the 2/3. So I'm starting on my right x value, which is y plus 2, and I'm ending on my left x value, which is y to the 2/3. Okay, so if you try and slice vertically, you're going to wind up with 3 different integrals. Very cumbersome. So here's my shaded area again, and I've got doing everything in terms of y's, and my integral is going to be, the area is the integral from, what are my y values? Y equals -1 to y equals 8 of my right x value, y plus 2, minus my left x value, y to the 2/3, dy. And so this is going to integrate to 1/2 y squared plus 2y minus 3/5 y to the 5/3 from -1 to 8. And what are we going to get here? 64 divided by 2, 32 plus 16 minus, what is this going to be? 32, 96 over 5, and then we're going to have minus 1/2 plus 2 minus 3/5. And so I think this winds up being 29 7/10, or 297 over 10. Okay. Last problem. We're going to find the area of the region bounded by y equals 9 minus x squared and y equals x plus 3. So 9 minus x squared is a parabola upside down. And I'm going to find the intersection points by setting these two equations equal to each other. Move everything over to one side. And I'm going to get x plus 3 and x minus 2 when I factor. The x coordinates of my intersection points are -3 and 2. And my ordered pairs are -3, -3, 0, and 2, 5. That kind of helps me figure out how I'm going to set the graph up. -3, 0. Remember, there's symmetry here. Okay, so let me just draw a light sketch first, and then I'll go back and fill in the graph. Okay. All right, so now you can see my bounded region is here. And there we go. And we've already got the intersection points. Again, right here. That's going to be 2, 5. And this, of course, 3, 0. And again, visually looking at this, I can see it's going to be much easier to do this in a single integral by slicing top to bottom. So my y on the top is the parabola, which is 9 minus x squared. My y on the bottom is the line, which is x plus 3. So my integral is going to be the integral from, we're doing everything in terms of x. An up and down slice is an x slice. So x is -3 to x is 2. And top minus bottom is 9 minus x squared minus x plus 3. That's going to integrate to 9x minus 1/3 x cubed minus 1/2 x squared minus 3x from -3 to 2. I'll just combine the two x's into a 6x. Okay, and I am left with here 12 minus 8/3 minus 2 minus, that's going to become a plus 18 minus 9 and then a plus 9/2. And I'm going to get 125 over 6 when I simplify that, which you can confirm for yourself.